Okay, hello everyone. In our last lesson, we learned about how X-rays are produced. We learned about Fmax, how we derive as Fmax, and we have tried questions solving for Fmax. So in this topic, we'll be learning about attenuation of X-rays and relate penetrating power of X-rays required to pass through a particular type of tissue to the energy and frequency of X-rays, and hence the potential difference across the X-ray tube. Okay, basically, photography. How does photography work, right? You have an object, and when you shine light onto the object is going to reflect light onto a photograph or photographic plate. So when you develop the photographic plate, right, what you see will be a negative image. Okay, this region of the panda is black. The reason is because when light strikes this region of the head that is white, it's going to reflect all colors of light, red, green, blue, and so on. So this white part of the head is going to reflect all types of light that strikes it. So when light strikes on the photographic plate, it causes an exposure on the photographic plate. So when you develop the photographic plate, it appears to be overexposed, becomes black. This region is white, and the reason why this region is white is because when light strikes on the arm of the panda, which is black in color, this black fur is going to absorb all light that strikes it. So what happens is no light will be reflected onto the photographic plate. So when no light strikes the photographic plate, there's no exposure. So when you develop the photographic plate, this region becomes white. So this is a negative image. So when you expose the negative image to light again, then you get a positive image. So how does X-ray produce an image, right? It's basically the image that you see is a photographic, it's using photographic, but it's using a negative image. Okay, there are three factors that determines the attenuation of X-rays. So what do you mean by attenuation? It means that the reduction in the intensity or amplitude of a wave whenever it passes through a medium. And attenuation depends on three factors: thickness, density, and atomic number. So I'll show you how each of these components, right, plays a part in the buildup of a X-ray image. So basically, this is your X-ray tube and this is your photographic film. So when you expose a photographic film to X-ray and you develop it, you find that the X-ray film will be exposed to X-ray, so everything will be black in color. So when you put, let's say, for instance, right, your leg, your thigh bone, right, between the photographic film and the X-ray tube, X-ray will pass through, right, your thigh bone, right? So regions where it passes through this region, you can see it passes through this region, it just passes through air. So there's no attenuation of X-ray at all. So when it strikes the photographic film, right, this is where you see there will be overexposure. So the photographic film will be black in color. But regions where it strikes the flesh and bones, right, it will cause attenuation of X-rays. So the flesh is made up of protein, and protein is basically made up of nitrogen, carbon, hydrogen, and so on, right? So what happens is there will be attenuation of X-rays. So that's why when you see part of the X-ray will be absorbed, part of the X-ray will be transmitted and it's going to strike the photographic film. That's why you see a shade of gray, right? Because part of the X-rays has been absorbed. So when you develop the film, you see your muscles, right? Can you see this? Here is a shade of gray. That means you see your flesh, right? When X-ray, parts of the X-ray that passes through the bone. So the bone is made of calcium, right? So calcium has a higher atomic number as compared to protein. So the attenuation of X-ray will be much higher. So what happens is you see majority of the X-rays have been absorbed. So this white strip means there's no X-ray that strikes the photographic film because all the X-ray has been absorbed. So when it strikes the photographic film, you find that this region has not been exposed to X-ray. So when you develop the film, you see regions of white. It means region of white means X-ray or the photographic film has not been exposed to X-ray. There's no exposure at all. Okay, let's take a bigger view, right? This is your thigh bone, and this is surrounding is basically your flesh. So if we look at the thigh bone, right, when you shine X-rays onto the thigh bone, and when you develop the film, right, you see the thigh bone, right, to be what you see here. You see the edges of the bone to be less exposed to X-ray as compared to the center of the bone. Okay, this can be explained by how X-ray moves through the bone. So let's assume, right, like this bone is of uniform thickness, and let's take that the thickness of the bone is 5 millimeter. So this 5 millimeter, this is 5 millimeter, and this is 5 millimeter. However, when X-ray passes through the edges of the bone, can you see when it passes through the edge here, it basically passes through 5 millimeter, 10, 15, 20, 25. Due to the way we position the bone, you find that the X-ray will pass through a thicker region of the bone. So when X-ray strikes the photographic film, the edges of the bone appears to be hardly exposed, so it appears to be very wide. But when X-ray passes through the center of the bone, so it passes through 5 millimeter, then it passes through soft tissue, that is your marrow, and then it passes through 5 millimeter again. So effectively, when it passes through the center of the bone, it is basically passing through only 10 centimeter of bone. So the attenuation of X-rays will be much less as compared to when X-ray passes through the edges of the bone. So you find that there will be overexposure right in the center of the bone as compared to the edges of the bone. There will be less exposure. Okay, so how does thickness, density, and atomic number plays a part? So this here is an X-ray of an ankle. We can see, right, that the bone, right, is actually made out of calcium, and this here is basically made out of stainless steel screws. So stainless steel, right, has an atomic number that's greater than the calcium of the bone. So you can see that where the bone lies and where the screw lies, we can see a big contrast between where the screw lies and where you see the bone. So this is how atomic number plays a part in the attenuation of X-ray. Thickness can be seen from, like in the previous slide, right? Although the bone is of uniform thickness, but how X-ray passes through the bone, right? When it passes through the edges of the bone, it appears to be passing through a thicker region of the bone as compared to when X-ray passes through the center of the bone. So we can see how thickness plays a part. Okay, this here is a dental X-ray. So we can see, right, atomic number, because this is your amalgam, right, the filling that you place inside your tooth if you have a cavity. So you can see that amalgam has a higher atomic number as compared to calcium. So the higher the atomic number, the higher the attenuation. Okay, thickness, okay, similar like bone, the edges of the tooth, right, appears to be hardly exposed in the X-ray film as compared to the center of the tooth. There's overexposure here, right? So we can see how thickness plays the part. Okay, density will be, basically we can see your tooth, right, is actually made out of calcium, and your bone is also made out of calcium. However, your tooth is made out of calcium that is densely packed. So it has a higher density as compared to the calcium that is inside your bone, right? So the density is much less as compared to the density of your tooth. So you can see the difference in density and how the higher the density of a material, the greater the attenuation. Okay, this is chest X-ray. So chest X-ray is basically made up of soft tissue, right? So what are the changes that the radiographer needs to make in order for you to produce a very good X-ray image, right? So it's basically made of soft tissue, your liver, right, your heart, and your lungs. Okay, this is a CT scan. So CT scan is actually taking X-rays of the head and your brains, right? It's actually enclosed by your skull, which is actually heart tissue. So actually it has to penetrate through your skull before you can see or take X-ray of your brains. Okay, so relate the attenuation of X-rays to the type of tissue. Right? So there are three factors that determines the attenuation of X-ray. And the three factors will be atomic number, thickness, and density. And I've showed you some X-rays of soft tissue, right, or bone. Okay, next, relate the penetrating power hardness of X-ray required to pass through a particular type of tissue. So whether are we taking X-ray of soft tissue or are we taking X-ray of the bone? So the hardness of X-ray has to change, right? So basically hardness is related to the penetrating power. So if I'm taking soft tissue like the lungs, I don't need very high hardness. I don't need X-ray to penetrate right through, right? Because it's all basically empty spaces. But when I'm taking X-ray of the bone, then I need very hard X-rays. And then relate the energy and frequency of X-ray and hence the potential difference across the X-ray tube. Okay, next is relate the minimum exposure time for X-ray photograph or given hardness to the intensity of X-ray and hence the tube current, which is determined by the filament current. Okay, so what's the difference between tube current and filament current? Okay, come back to an X-ray tube. Okay, when I close the switch that controls the filament current is going to flow through this filament. It's going to heat up the filament and then go back through this battery. So when current flows through this filament, it's going to heat up the filament and it's going to produce electrons by a process that's known as thermionic emission. So there'll be a cloud of electrons surrounding this hot filament. Next, I switch on the power supply, the high tension power supply. So when I switch on the high tension power supply, I create a high tension potential. Okay, this is a simplified view of the high tension potential. It actually goes through a rectifying circuit to make this direct current, right? So what happens is this direct current will make the target positive. So the electrons are negative, will be attracted towards the target because the target is at a positive potential. So in this case, the electrons will be attracted, they will gain kinetic energy. So in the process, when they gain kinetic energy, when they collide with the target, they will lose kinetic energy. And that's where they produce X-ray photons, like what I described in the previous part. Okay, filament current is this current, the current that flows through the filament. Tube current will be, all right, this thing. You see, when electron moves from the filament towards the target, electrons are charged particles. So current will be basically the motion of positive charges. So when electrons, they are negative charge particle moves from the filament towards the target, current is actually from the target towards the filament. So this current is known as your tube current, and this is known as your filament current. So when electron strikes the target, then you have a lot of X-rays that's being produced, right? Okay, so there are two settings. One is your filament current, and one is your tube potential. So in the first experiment, if I set my tube potential constant, it means I set this to be constant, and I change my filament current, that is the current that flows through this filament, right? This is the filament current. So what I get will be, I get a spectrum like this, X-ray spectrum. So what I see is a continuous range of frequencies, right, of high energy X-rays as well as low energy X-rays. So when I increase the filament current, my intensity increases, but my F max remains unchanged. Okay, the question is, why would F max remain unchanged? The reason is because maximum frequency of X-ray depends on the tube potential. This is your tube potential. So if I keep the tube potential constant, E and H are constant, tube potential is constant. So in other words, F max will be constant. So when I increase the filament current, I2, which is greater than I1, F max remains unchanged. But what changes is the intensity of X-ray. Let me say if I'm interested to find, let's say, this frequency of X-ray, F frequency A, let's call this frequency A. At tube potential I1, I get this intensity of frequency A. When I increase the tube potential to I2, at this same frequency, I get a higher intensity. So how did Einstein explain about intensity? He explained that intensity is referring to the number of photons. So this means that there's a higher number of photons that's being emitted when I increase the filament current. So when I increase my filament current, right, what actually happens is, you see, if I set I1 low current, it produces electrons, all right, by thermionic emission. But since this is low current, the filament is not as hot as it is, right? So the number of electrons that are produced are very, very few. So when I increase my current to I2, where I2 is much higher than I1, that means the filament becomes hotter. So when the filament is hotter, then more electrons will be produced. So by producing more electrons, what happens is if there are more electrons striking the target, then there'll be more collision. If there's more collision, then there'll be more photons that's being produced. So this will account for why will the intensity of the X-ray increase when I increase the filament current. Because when I increase the filament current, the filament becomes hotter. As the filament becomes hotter, more electrons are produced by thermionic emission. So if there are more electrons produced, more electrons will strike the target, and more photons will be produced. So more photons means higher intensity. Okay, if I keep on increasing I3, intensity will increase further. Okay, I3, higher number of electrons. So more electrons, more collision. If there's more collision, more photons will be produced. Okay, the next thing is if I keep the filament current constant when I increase the tube potential, this is spectrum that I will see. Right? Again, I'll see a continuous range of frequencies from low energy X-rays, low frequency, to high energy X-ray, high frequency. Okay, think of this is tube potential V1, this is tube potential V2, this is tube potential V3. So V1 has the lowest potential. So naturally, you will have the lowest maximum frequency. When I increase the tube potential, frequency maximum increase. When I increase the tube potential further, frequency maximum increase. And this can be explained from this formula. When I increase the tube potential, I increase Fmax. Okay, intensity will also increase. All right, at tube potential V1, this is my intensity. This is my intensity at tube potential V2, and this is my intensity at tube potential V3. Okay, why would intensity increase? If I keep my filament current constant. Basically, if I keep the filament current constant, I'm limiting the number of electrons from the filament. So if I limit the same number of electrons, that means they'll go through the same amount of collision. So I would expect that the intensity should be basically the same. But why would my intensity increase? Okay, this can be explained by, let's consider a thought experiment. Let's say, for instance, if you have a ball, so if you drop a ball from a certain height, the ball is going to bounce, all right, the floor, and each time it bounces, it loses energy. So when it loses energy, it's releasing energy in the different form of energy, like X-ray. When X-ray strikes a target, it loses energy. So it loses energy in the form of X-ray photons. So what happens if I have a ball of higher energy? So if I drop a ball from a point that's much higher, so this ball is going to strike around and it's going to bounce many times more before it stops. So if a ball has low energy, it just bounces maybe 2 times before it stops. But if a ball has more energy, it's going to bounce many more times before it stops. So the same case like the electrons, right? If electrons have higher energy, it's going to go through multiple collisions with the target before stopping. So the more collision that it makes, the more photons that can be produced. So that's why intensity would increase, right? Okay, characteristic lines, all right? I'll explain this in subtopic 3.3. What causes these characteristic lines when the tube potential becomes large? Typically, we get characteristic lines when the tube potential is 100 kilovolts and above, right? So when the tube potential is 100 kilovolts and above, that's when you start seeing these characteristic lines. Okay, so what are the changes that the radiographer needs to make, right, to the filament current as well as the tube potential? So let's take for instance, if the first patient that comes in and the radiographer wants to take an X-ray of the thigh bone. So what the radiographer needs to do, right? The thigh bone is basically made of bone, so it's basically hard tissue. So we need high energy X-ray in order for us to see very clear images of the bone. So to see clear images, we need high energy X-ray. So what we need to do would be, we need to increase the tube potential, this thing. So when we increase the tube potential, we produce high energy X-ray. So we call them as hard X-ray. So this hard X-ray is able to penetrate the bone and causes an exposure on the photographic film. We are not interested to see the flesh that's surrounding the bones. So the doctor is only interested to see whether there's damage to the bone and so on. So we need to use hard X-ray. But the problem is when you start increasing the tube potential, the intensity starts increasing. Right? So if the intensity starts increasing, then there'll be more photons striking. Eventually, this whole film becomes black, and you don't see the contrast between the bone and the surrounding flesh. So to avoid that, the radiographer needs to reduce the filament current, because by reducing the filament current, you decrease the intensity of X-ray. So when you increase the tube potential, you increase the energy of the X-ray as well as you increase the intensity. But if you want to have high energy X-ray with low intensity, so the radiographer has to reduce the filament current. So then you take a very nice X-ray image. But what happens if the next patient that comes in and this patient, right, went to see the intestines, right, or the abdomen of this patient? So this patient is already gone, right? You have already taken X-ray. Now the next patient that comes in, you want to see the intestines. So in this case, we cannot use hard X-ray because the intestines are basically soft tissue. So if you set your settings like patient 1 just now, all this hard X-ray is going to pass right through the soft tissue. So what happens is this whole film becomes black. So in order for us to see soft tissue, we have to use low energy X-ray. So in this case, the radiographer has to make use of the setting again, such that the radiographer has to change the tube potential to low potential. So when you reduce the low potential, you're actually producing low energy X-ray, or is known as soft X-ray. So soft X-ray can be absorbed by soft tissue, right? But what happens is when you lower the tube potential, the intensity drops so much so, right? If the intensity is too low, then you don't see an image at all. There's no exposure on the film and the whole film becomes white. So to cause the film to have a decent amount of exposure, the radiographer has to increase the filament current. Because when you increase the filament current, you increase the intensity of X-ray. So the radiographer needs to make changes to the X-ray tube, right, the tube potential as well as the filament current, depending on what's the target that you want to take. If you want to take, let's say, X-ray of the bone, then you need high tube potential. If you want to take X-ray of soft tissue, then you need low tube potential. Okay, so clear about relate the minimum exposure of X-ray or the ground or given hardness. So hardness will be the penetrating power. Hard X-rays are high penetrating X-rays. Soft X-rays are basically low energy X-rays. So what has frequency or energy of photon related to intensity? So intensity is referring to the number of photons. So we can increase the intensity of X-ray by increasing the filament current. Okay, and filament current, right? Filament current